Welcome. In this video I'll discuss Whistler waves, which are kind of parallel wave which we discovered in the last video, looking at the cold plasma dispersion relation. So these waves which travel along magnetic field lines, and they're observed first in radio signals, so first around the 1890s when long distance telegraph poles were set up. People picked up signals, and these were descending notes in the audio frequencies, sounded like whistling, and so hence these became known as Whistler waves. In plasma physics, these are also called helicon waves, and I'll discuss these in a next video on how they're used to heat the plasmas or to inject power into plasmas. This video I'll concentrate on the ionospheric, so the atmospheric observations, so from radio waves, and their basic properties. We'll look at things like their dispersion relation, their group velocity. They have some interesting properties that the faster frequencies travel quicker, so the higher frequencies travel quicker. And so if you have a source of waves, for example a lightning strike, and these waves travel along field lines, the higher frequencies arrive first, and so what you hear is a descending note. So you hear the high notes first, and then this descends into low notes. And if you Google for NASA sound cloud Whistler, you'll find some very interesting sound recordings of what these waves sound like. And there are some interesting phenomena. So it turns out there's a maximum in the speed, and these are, in the old literature, these are called things like nose whistlers, and these are used for analysing the ionospheric plasmas, so trying to infer what the density of the ionospheric plasma was by using these Whistler waves. And so I'll start by looking at the dispersion relation. So this was for the refractive index, which is derived in the previous video. So you write down an expression for the refractive index for the parallel direction. And this is just the square of the k vector along, so parallel to the magnetic field. This is all squared here. I'll just put this whole thing squared. So this is the refractive index, so k along the field line, and the frequency. And for a right-handed wave, this is approximately given by this expression where you have pi e is the electron plasma frequency, and then we have the frequency of the wave. We have the frequency of the electron cyclotron and the frequency of the ion cyclotron wave. Ion cyclotron, omega I here. So here omega E is negative, so it's minus E. It has the electron mass. Note this is less than 0. And omega I is the ion cyclotron frequency, so it's EP over MI. So there's a Z here if there's more than a charge bigger than 1. And then pi e squared is n e squared over epsilon naught me. So this is the electron plasma frequency. This is an approximate expression, so there should be kind of wiggles here, but it's pretty accurate in most cases. It has several interesting limits. So the first one is just the very low frequency. So if omega here is much less than the ion cyclotron frequency, so if omega is much less than ion cyclotron frequency, this whole thing reduces to alphane waves. We show this fairly easily that this here, omega plus omega e, becomes just omega e. This omega plus omega I is approximately just omega I, and so we have the n parallel squared is roughly like 1 minus pi e squared over, now we have omega e omega I, and we just put the expressions here into this formula. And so we have just an e squared n e, so this is electron density over epsilon naught me, and then we multiply by the inverse of the ion electron cyclotron frequencies. So here you have an me, and we have a minus eb, and we have an mi over eb. Just assume that the charge is 1 for now, just to keep things simple. So the electron masses cancel, the electron charges cancel, and now we have something which is starting to look like an alphane frequency with a density and an ion mass. And so we can just write this as, well, here we just need a mu naught at the bottom here, and a mu naught and epsilon naught make c squared, so mu naught epsilon naught is 1 over c squared, and so we can just write this whole thing. So here we have an n to m So we have an n mi, you have to take a mu naught here, over b squared, and this is 1 over alphane speed squared, and then we have left over, we have a mu naught times epsilon naught, which makes a 1 over a c squared here. So c squared. This is like 1 minus c squared over v alphane squared. And this whole thing is just c squared k parallel squared over omega squared. And now we just see that what we have here is that k parallel squared over omega squared is just 1 over c squared. So it should be a plus. So this minus here makes this a plus. So it becomes a plus here. So it's plus 1 over v alphane squared. And of course, c squared is much larger than alphane speed squared, and so that can be neglected. And this is just an alphane wave. So in the low frequency limit, below the ion cyclotron frequency, whistle waves are just alphane waves, and the same thing works for left and right-handed. I just showed for the right-handed one, but it's the same thing for left, and they both reduce to the shear alphane wave. So the next interesting regime is the intermediate regime. So if we're between the ion and electron cyclotron frequencies, then we can essentially take out the ion, so above the ion, so frequency is above the ion cyclotron frequency, but much less than the electron cyclotron frequency. Then we can write down that in parallel squareds, so we have again the electron plasma frequency, so omega plus omega e here, and I have omega plus omega I. So now if omega is much bigger than omega I, this part here just becomes omega, and if omega is much less than omega e, this part just becomes approximately equal to omega e. And so we can write down where I assume that pi e is large, and so I can neglect this one at the front. And so here we have an expression. We can put the expressions we had before into this formula, and we can just write this out. So this is a dispersion relation which links the frequency to the wavelength, and now from this we can work out group velocities and phase velocities. So the group velocity, which is the velocity that the information or energy is transferred, is d omega by dk, or in this case dk parallel because it's propagating along a field line. And so we can differentiate this formula with respect to k parallel, and so you just end up with a 2c squared k parallel on the left, and then on the right we have pi e squared over omega e d omega by dk parallel. And now we can substitute in this, so we have an expression for k parallel here. We can just take this k parallel and substitute into there, and you can see you end up with a square root of omega factor on the left hand side here. And so we can rearrange this and write it out a bit more neatly, that we have d omega by dk parallel in this case is roughly 2 times the speed of light times square root of omega. Now the magnitude, because the omega e electron cyclotron frequency is negative, so it's the magnitude of that divided by electron plasma frequency. And so this of course is just proportional to square root of omega. So the higher frequency waves travel faster, and so what happens in the Earth's atmosphere is if you have the Earth like this, we have magnetic field lines which come out around here, and what would happen is you can have a storm, for example, electrical storm, so you have lightning producing whistle waves, and they travel along the magnetic field. So this is B. They travel along the Earth's magnetic field and like this, and then be received on the ground at another location, And what would happen is that if you had a lightning strike, this is like a delta function, it generates a wide range of different frequencies. These frequencies all travel together, but because the higher frequencies travel fastest, they arrive first. And so what you'd see, what you'd hear on the radio, is if this is frequency, this is time, you'd find that the highest frequencies arrived first, and then the other frequencies would arrive later. And so you'd hear a falling chirp or falling whistle on the radio, as you typically repeat. So you'd end up with many different chirps and whistles on the radio, and these are in the kilohertz range. So typically, kind of 1 to 10 kilohertz, which is in the audio range, so that these could be heard by ear on radio. Now these are used to calculate the structure of the magnetic field. So if you have so before the day of satellites and so on, if you wanted to work out what the density of the plasma, say in the ionosphere was, you could use these waves and the characteristics of these waves, because the time delay. So if this is the velocity, the time delay is basically proportional to the integral along this path of the square root of this factor here. And because of this square root of cyclotron frequency dependence here, this integral is most sensitive to areas where this is small. So this is like a weighting factor, and where pi e is small, this will have the highest magnitude, and so this will essentially be weighted to the regions which are furthest from the Earth. And so this integral depends mainly on the cyclotron frequency and the plasma frequency at the top of this loop. And so this is used to try and infer the plasma frequency and hence the density at the top of this magnetic field loops. So the dispersion relation for this right-handed wave and the left-handed wave looks like this. So we have k on this side, we have omega, and then we have different waves that we can relate to. So this is the light wave, this is c. Here's the alphane wave, the alphane, and so this is the limits. We have very low frequencies, it looks like the alphane wave. We have some frequencies here that are useful. So this is the ion cyclotron frequency, and here I have the electron omega e, modulus because it's negative, but this is the electron cyclotron frequency. And what we have is several different branches. So the left-handed branch I'll do in red. So what this looks like is we have basically looks like the alphane wave at low frequencies, then the frequency is increased, and then it actually levels off at the electron cyclotron frequency. And at this point, what we have is that n in parallel squared goes to infinity, and this is where it's absorbed. So these whistle waves are absorbed at the electron cyclotron frequency, and these come sometimes called R waves or the electron whistlers. Because they're right-handed and they're absorbed at the electron frequency. Now above the electron frequency, there's a period where the waves are evanescent and don't propagate, and then at high enough frequencies, these become again the light wave. So at high frequencies, the waves propagate again. The other kind of parallel waves is the left-handed waves, and these also look like alphane waves at low frequencies, but then these tail off, and these are absorbed at the ion cyclotron frequency. And these are called L waves or ion whistlers. And again, at high enough frequencies, these also propagate again. So if you go up to some frequency up here, then these will again propagate and become like light waves at high frequencies. Okay, there's one final more curiosity really, but of historical use, is in order to analyze these, to analyze the ionosphere, you have factors involving the cyclotron frequency and the plasma frequency, and so you need some way of separating the effect of cyclotron frequency from plasma frequency. And one way of doing this is to use a subtlety of the the dispersion relation, which is that there is actually a maximum in the frequency, in the velocity, and you can see this if you take omega is approximately the electron cyclotron frequency. This is kind of a new topic. So we're taking the right-handed waves in the vicinity of this region here. So it's not quite absorbed, but it's just coming up to here. So high frequency right-handed wave. What we can do is write down that the parallel refractive index is roughly like we had before. So now we have the electron component, so pi e, and now omega is much larger than the ion cyclotron frequency, so omega, the ion cyclotron component can be neglected, and this we can just multiply through by omega, and so we have that c squared k parallel squared is just minus, now we have a pi e omega e like this, so just a factor of omega e of omega here becomes this omega, and multiply through by omega squared. And now we do the same thing as before, we just differentiate this with respect to omega, and then rearrange it a little bit, and I'll write this out. So it's the same process as before, we just differentiate this formula, and we end up with these different terms. Now we have two terms involving d omega by dk parallel, and we just substitute this equation here. So for k parallel into this k parallel, for example, and that becomes that. This term here in square root is just from this, and also of course from here, this term here has gone to here, and now we're going to substitute in this c squared k parallel squared becomes this, and then these two terms here together you can write out. So here we have a, try and keep this on the screen. So here we have a minus, I'll just do this part here. So this is going to be a minus pi e squared omega. Then we have a pi e squared here. And I'm going to try and put everything over omega plus omega e. So we have omega e, pi e here, so we have pi e, again omega plus omega e. And you see some of these terms will cancel. This pi e squared. So this term will cancel that term, for example. Here we just have a pi e squared with an electron cyclotron frequency here. And so this is just pi e omega e over omega, move this up here, so omega e. Okay, so this then simplifies a bit. So we've removed all the k parallels, and we just have an expression before for d omega by dk in terms of omega and all these frequencies. And so we just simplify this to here, for example, we have an omega plus omega e, and so this is a square root. We have this omega plus omega e over here, and this we can move over to the right hand side. And so we end up with omega plus omega e to the 3/2 on the left hand side, with the square root of omega here. So we have a 2c squared from there. We have a square root of omega. We then have omega plus omega e times omega plus omega e divided by the square root. So it ends up being omega plus omega e to the 3/2. And that is approximately equal to, well, here we have a pi e squared, here we have a pi e squared square rooted, and so here we have just left with one factor of pi e. There's a minus sign still here. Does this omega e come from here? Let's put squared here. And we have d omega by dk. Okay, so I have slightly more complicated expressions. So previously we didn't have this factor here, but now we have two factors of omega. What this means is that there's a maximum in omega, because this goes to 0. So this goes to 0 as the frequency. So as omega, the frequency goes to the electron cyclotron frequency, the group velocity goes to 0. So we have that d omega by dk parallel goes to 0 as omega goes to omega e, so as it goes to being absorbed, and therefore there must be a maximum, so maximum velocity. And you can quite easily work this out. So take the differential to differentiate this with respect to omega, and you can show that the maximum group velocity is at omega. Omega is a quarter of the electron cyclotron frequency, and this maximum group velocity allows you to work out what the electron cyclotron frequency is, and then you can use this to again, if you put this back into the formula for the for this, so time delay, you can use, if you know something about the electron cyclotron frequency, you can use this to infer what the plasma frequency is, and therefore calculate the density. And so what you'd end up with on a frequency versus time, versus frequency, you now have there's a maximum, so this is a quarter e. So the first frequencies to arrive would be these fastest ones, and then you'd find the other, so lower frequencies as before, but you also find the higher frequencies as well. And of course there's a cutoff here at omega e where it's absorbed, and so you have this sort of rising and falling frequencies as well, and these are called nose whistlers. So there's quite a lot of studies of these whistlers, because it allowed you to infer the electron cyclotron frequency from this first sort of fastest arriving frequency, and therefore infer properties of the plasma. Okay, thank you.